Okay, we're being recorded now. All right, so thank you everyone for coming back. So last week we started going through just Carlson and Mellett's paper on the shuffle conjecture and how they proved it. And in essence, what we did is we constructed a bijection from the usual formulation that we saw in the seminar so far in terms of area and div into these new statistics called bounds and inv, right? And we also pointed out that the thing that they proved was not directly the shuffle conjecture, but a refinement of it known as the compositional shuffle conjecture. So just so that we're on the same page, as a reminder, right? So recall that the shuffle conjecture is the following statement. So it's, well, this is really fat. So it's the statement that -1 to the n nabla en is the sum over t to the area of pi. So this is just kind of a review so that we're all, again, on the same page. Pi w of x to the w, where w is a word parking function. And then here, this is a dig path, an n by n dig path, right? Okay, and then the compositional shuffle conjecture which is a refinement of the one above. So, right, this one is due to HHL and then UR, I think. And then the compositional shuffle conjecture is going to be Hagelin, Morrison, Zabrocki. So what they said is basically, instead of taking nabla of En, you're going to take nabla of this operator C alpha. I didn't tell you what it is. I will tell you hopefully today. But it's some other slightly more complicated operator. It's not just a symmetric function. And what they said is that this, rather than summing over all dig paths, you're going to only sum over dig paths whose touch points are indexed by this composition alpha, right? And the rest of the sum is the same. Ooh, it doesn't fit. So the rest of the sum is the same. Okay, and these statements were shown to, or if you prove the compositional shuffle conjecture, then you prove the shuffle conjecture by basically just summing over all possible touch points or arrangements of touch points, right? So what they did in the first part of the paper is basically rephrase this area and div to new statistics. So what they proved is that this is in fact equal to some new statistics that we're going to call touch prime of pi prime, right? Because they constructed a new dig path based on this permutation. Then they constructed a new statistic called bounds of pi prime, which they showed could be exchanged with area of pi. So bounds of pi prime was equal to area of pi. Then here you had q to the inv now of pi w, and then this stays the same. And recall that the definition of our word parking functions changed slightly. It turned out to be equivalent under this mapping from pi to pi prime, but it was no longer just reading words and making sure that they were decreasing as you read them up the columns. It was a bit more complicated. So this is our new version. And so what we're going to focus on is proving this. So to do that, we're going to label this new formulation in terms of bounds and inv. We're going to call that d alpha of qt. And our goal is to study d alpha of qt as a function of pi. Okay, so to do that, we're going to do something a bit more general. We're going to generalize the internal sum of this thing. So I apologize in advance. There's a couple of proofs that I'm going to have to go over, or either just sketch or skip entirely because it's a lot of material. But either we can discuss it later, or you can, of course, read the paper. Okay, so we're going to talk about characteristic functions of dig paths. So that's what the. So in order to do that, we're going to define a more general. So let's define a more general formula for version of this, a more general function, where instead we're going to call this, so chi of pi 1, we're going to let this be the sum over q to the n of pi w. So up to here, it looks like we're doing exactly the same thing. But instead of summing over just word parking functions, we're going to sum over any word. So just any word, so no constraints on it. And the claim, I guess I'll do it in orange. So the claim is that this function, chi of pi 1, is actually a symmetric polynomial. Now, this is not obvious, and it does require a proof. Like I said, if we have time, we'll do it as an exercise at the end. But it's a non-trivial check. But you just do it directly. And a comment is that this is actually just an example of an LLT polynomial. So if you can prove that it's an LLT polynomial, you obviously get the symmetry immediately. So just as a note, is that this is just an LLT polynomial. Okay, excellent. So we're actually going to generalize this even further. So how are we going to generalize this even further? Well, we're going to consider something that's known as a weighted characteristic function. So weighted characteristic function for dict-pats. And we're going to do that by introducing a weight function. So we're going to let the weight function be a function that's defined on the corners of pi. Remember, we defined the corners of pi in the previous part. Just as a reminder, the corners of pi, where if you had pi prime, right, we had pi, then you constructed pi prime. Then the corners of pi were these cells, right? Okay, so you have this set, and you're going to define on those sets, or on those cells, a weight function that goes into some space R, and we're going to let that be a weight function such that so that we can set chi of pi of the weight. So this is to be the following function. So it's going to be q to the n of pi w times the product. So this is kind of a nasty formula, so I apologize. Times chi of w. And here, we're going to sum over all cells in your corner, in the set of corners, such that wi is less than or equal to wj. And then here, we're still summing over all possible words, not just word parking functions. So this seems kind of like a weird thing to do, but you'll note that if we set the weight equal to 1, right, so chi of pi 1 here, when the weight equals 1, recovers the expression above, right here. So this is really truly is a generalization of the thing above. So recovers the polynomial above. Ooh. Okay, and in particular, we also get that when we have pi equal to 0, so if the weight, so if the weight equals 0, we actually get exactly what we wanted before. So we get that d alpha of q of t can be written then as t to the bounds of pi times chi of pi 0. So, right, if you, in this formula, consider the equation when the weight is equal to 0, you actually get exactly the definition of these word parking functions primed, right? So it's not hard to see. Essentially, so maybe let me add a line to explain why that's true. So if you think of chi of pi, right, this more general function, if you just sum over words that are in, minus, like, so that are words but that are not in the complement of of word parking functions primed, right, times the stuff inside. So q to the inv, et cetera, pi w, et cetera, chi w, and then plus, and then you sum over things that were in word parking functions, q to the inv of pi w. You'll notice that if your weight was 0, then this, right, is exactly basically counting the things that were in the complement of word parking functions prime, because this condition here is exactly, it's basically saying that w is in the complement, let's say, is in the complement of wp pi prime. So what that means is that if your weight is 0, then okay, w, that it means that this part is just 0, and what you get is exactly just this part, right? You get this back. Right, which is why you can just substitute this back into, maybe let me write 0 here. Does that make sense? So you really do get this equation back. So what that means is that we want to study now chi of pi 0 and chi of pi 1. Okay, so now there's another claim. And the second claim that they make is that not only is chi of pi 1 and chi of pi 0, not only are these symmetric functions, but in fact, the more general construction is. So this chi of pi weight for any weight is in fact a symmetric function. So how do you prove that? So I'm going to give you a sketch. So what's the sketch of the proof? So the idea for the proof is that you notice that you can write chi of pi of the weight. You can decompose this as a sum over 2 pieces. So I'm going to write a formula, weight of ij minus 1 over q minus 1 times chi of pi, and we're going to call this weight 1, and I will tell you in a second what this is saying, plus 1 minus weight of ij over q minus 1 times chi of pi, let's call this double prime, weight 2. So what is weight 1? What is weight 2? So here, let me pick a different color. So here, weight 1 is the same as weight. So weight 1 equals weight for all cells except ij, with weight 1 of ij equals to 1. So it's basically, you take the original weight function, whatever it was, you're picking an ij, and you say, all right, for that ij, let me define a new weight function that sets the weight of cell ij equal to 1 and leaves everything else the same. So that's weight 1. Now, pi prime is pi, so pi prime equals pi with the...
Sorry, wait, I just want to check. So ij is some fixed cell, and is it a corner or a non-corner?
It is a corner. ij is a corner. Yes, okay. Thank you. So idea, yes, that's an important point. Sorry. So here, ij is in the corner, the set of corners. Absolutely. Thank you, Monica. Yeah. And so then pi double prime is the same as pi, except you take that corner and then you flip it. So with the corner ij flipped, I'll do an example, and I think it'll become apparent what's going on in this formula. And then weight 2 is essentially, it's the same thing, but then you set, you basically just set all the weights except of that corner equal to the same thing. So it's the same thing. You're basically trying to translate the weight, this arbitrary weight, to weight 1, so that you can write chi of pi of weight in terms of a sum of chi of pi 1. So let's do an example. Because, or sorry, and then the idea, yeah. So then the idea is that with this formula, then you can recursively apply it. You can recursively apply it to any weight and write chi of pi weight in terms of chi of pi 1. But chi of pi 1 is a symmetric function, therefore chi of pi of weight is also a symmetric function, which implies that chi of pi weight, whatever, is also symmetric. So let me do an example of.
Wait, I have a question also about the first term. So you have q times weight ij minus 1. Is that?
That is correct.
Okay, so there's not a parentheses there. It's q weight ij and then all that.
Yes. Q only acts on the weight ij, not on the 1. Exactly. So let's actually do this and let's see what's happening. So let's do an example. So suppose that pi is the following. So we take 3 north steps, then we do an east step, then we do a north step, we do 2 east steps, north, and then 2 east. So what are the corners of this set? So the corners are this one and this one. These are my corners. All right, so C of pi is 1, 4 and 3, 5.
So I'm confused. Is it a pi or a pi prime?
So because that's a good point. So basically, the pi that we were dealing with at the beginning is never to be seen again. And all of the introduction was basically saying all the pi's that we had, we're just going to always deal with these new pi primes. So whenever I write pi, I mean pi prime, because we're never going to see the pi's again. Does that make sense?
Okay. Yeah. Okay.
Sorry. Yeah. So basically, this part was just saying we changed terminology. All the old stuff got translated to new things. Therefore, let's just drop all the primes because they're irrelevant. Yeah.
Okay, thank you.
Yeah, sorry for the confusion. So now, suppose we're given some pi with these new statistics that we talked about in the previous meeting. And what we want here, suppose we wanted to express chi of pi 0, suppose our weight was 0, in terms of chi of pi 1. Right? How would we do that? And the idea here is that you use this formula. So, right, our initial weight is weight equals 0, which means, in particular, that the weight of 1, 4 equals 0, and the weight of 3, 5 equals 0. And so we're going to write, all right, chi of pi 0, according to that formula above, is going to be q times the weight of 1, 4. So let's suppose we're working with corner 1, 4, minus 1 over q minus 1 times chi of pi of weight 1, or here, right, here, weight 1 of 1, 4 gets flipped to 1 because the ij in consideration is 1, 4, but weight 1 of 3, 5 remains 0 because that's not the one we're considering, so we're going to leave it as it was. And then we're going to add 1 minus the weight of 1, 4, which by the way is 0, right? Because, so this is actually 0, and this is actually 0, over q minus 1 times chi of pi double prime. I'll tell you what chi double prime is in a second, times weight 2. So what is chi double prime? So here, chi double prime is the following path. So you're going to take, so this was the corner 1, 4, and you're just going to flip it. So copy, paste. And what I mean by flipping it is I'm going to take my path and flip it. So I'm going to literally just flip the corner inside out. Right, and now pi prime has one less corner, or sorry, pi double prime has one less corner than, or one fewer corner, whatever, one corner less than pi originally, right? And then the weight 2, so then here, weight 2, well, weight 2 is only defined on one corner because there's only one corner left. And so then here, weight 2 of 3/5 is going to remain 0 because you're not going to change that. And if we had generated new corners, which in this case we didn't, but if by flipping that corner we had generated new corners, then those new corners would get weight 1. So weight 2 of ij is going to be 1 on any new corners ij that may be created, that are created. Okay, and then basically you do it again, right? And so then you proceed and you do it again, but now on this function. So this function has a mixed weight, so you want to change that weight 3/5 to so that it's weight 1. Essentially, you want to change everything recursively to 1. So then you do it again. So then you say, all right, chi pi of weight 1 is going to be what? Well, it's going to be q times 0 because this is the weight 1 of 3/5 minus 1 over q minus 1 times chi of pi. Let's call it weight 1/1, right? Or what is weight 1/1? Well, weight 1/1 basically sets, where's weight 1/1? It has weight 1/4 equal to 1, and then since we're dealing with corner 3/5, 3/5 gets sent to 1. So weight 1/1 is really just 1. It acts like 1 on everything. Right? Okay. And then we add the second part, which is 1 minus, again, 0, because the weight of 3/5 is 0, over q minus 1 times chi of pi double prime, weight 2, 1, 2. So what is chi double prime? Well, or sorry, triple prime. So copy. No, sorry, this one. Copy, paste. So chi triple prime is you take pi and you flip, instead of 1/4, you flip 3/5, right? So here we flip this one instead. So that's our other corner. And then you'll notice that in doing this, you generated a new corner, right? When we flip 3/5, now we have a new corner. So this is a new corner. But that's okay, because the instructions say that if we say generate a new corner, we just set the weight equal to 1. So it's not a big deal. And so then we notice that what that means is that then weight 1, 2 is basically just taking everything and setting it equal to 1. So weight 1, 2 is also 1 because the new corner is 1. Weight 1/4 was already 1 because it came from weight 1. And then the new corner just got set to 1. So weight 1, 2 is 1. Great. This is equal to 1. Okay, so then that transformed the first part here. This transformed chi pi of weight 1 to a sum over chi pi for maybe pi or pi prime, whatever. But the point is that the weights are 0. And then we do that again for the second part. For this, we do that again for this term, where we need to we need to flip the 3/5. Right? So we continue, and I'll do it one more time just for the sake of finishing the example.
Can I interrupt
yes.
before you continue? So so the function weight, was this function on self, and it went to it could take any values, any real values.
Yes.
I mean, here there's just zeros and ones, but it could be like 7/3 or something like that.
Yes, yes. Sorry, I did it. This should be an R.
Okay.
Yeah.
All right. Yeah, I have to think about this a little bit. If they weren't just zeros and ones, why everything still works. But,
I think in practice, we're just going to deal with zeros and ones. So whatever. But I think it's definitely more generally defined. And the formula doesn't assume you're in zeros and ones. It just says you can transform everything to 1, essentially. Okay, so let me just finish. And then what we get at the end, and then if we do chi of pi double prime of weight 2, right? We do the exact same thing. We get this is q times 0 because this is the weight 2 of 3, 5. Right? Minus 1 over q minus 1 chi pi double prime of weight 2, 1, where weight 2, 1 basically just sets the weight of 3, 5 equal to 1. It used to be 0, and now we're setting it equal to 1, right? So then what that means, so maybe let me do this in orange. What that gives us is that this is now just equal to, so weight 2, 1 is really just 1 because you've successfully transferred everything to 1. And then you play the same game with the last piece, right, where this is chi of pi, I guess, quadruple prime because we have triple prime already, weight 2, 2, and once again, weight 2, 2 because it's just setting everything equal to 1 is just going to be weight equal to 1. So this is just 1. And then in this way, you've basically shown that you can go through and rewrite everything. So you can take this chi of pi 0, and I'll let you do the computations yourself, but you actually show that this becomes 1 over q minus 1 squared times chi of pi quadruple prime 1 minus chi of pi triple prime 1, because the double primes cancel. So the double prime that shows up here ends up canceling with the double prime that showed up at the beginning somehow. And that's basically it. The argument is you can use this formula to rewrite whatever weight you want into chi of pi 1, or a sum over chi of pi 1s. Okay, great. So now we're going to change kind of directions entirely. Because in order to actually prove the shuffle conjecture, we need to introduce some new machinery. And what we want to do is to show that we can generate these chi pi's 1s and chi pi 0s using this new machinery, or this new algebra that they define. So it's a little bit definitional heavy, so just bear with me. So this is section 4 in the paper. It's called raising and lowering operators. So I should stick with a color. So raising and lowering operators. Okay, so what's the idea? So we're going to set dkn to be the set of Dick paths from 0k to nn, right? So we're starting kind of after having taken k north steps. So these are known as partial Dick paths. We're going to set dk to just be the union of all these over all n. So you're still starting at level k, but you can be as long as you want. And then we're going to let this be the number of north steps. So it's n minus k. So this is the number of north steps. Okay. And our goal is to build a recursion for this dk. So how do we do that? So in order to do this, we're going to define an extension. So the goal is to define an extension of chi from Dick paths to this new vector space we're going to call vk. And then we're going to prove that there's a family of operators on vk, so some operators here, that essentially commute with adding north and east steps. So there exist operators that commute with adding, and I'm going to put that here in parentheses, north, east steps. Okay, So let's define this new vector space. So definition. We're going to define VK to be our ring of symmetric functions x tensored with just a bunch of polynomials or a bunch of extra variables y1 through yk. So here, just recall that this sim is, we're working with symmetric functions over q, t, right? So symmetric functions with coefficients in q and t, and we're just appending a bunch of variables y1 through yk. And we're going to define some operators. So define the operators. So we're going to define the operator ti. So ti is going to be an operator from vk to vk, where I is going to range from 1 to k minus 1. So you have k minus 1 operators on vk. And they're going to define, their action is going to be defined as follows. So ti of f, if f is a function in vk, is going to act by taking q minus 1 times yi times f plus yi plus 1, plus 1 minus q times yi, and then si of f. Si of f is basically saying take f and then swap yi and yi plus 1. So it's just the action of the symmetric group on it. And then you can divide that by yi plus 1 minus yi. This function has an inverse, so there's actually a ti inverse that's also defined. So ti inverse of f is almost the same thing, except you divide by 1 over q, and then you swap a sign. So it's almost the same thing. Let me get the sign correct. Oh yeah, sorry, you don't swap. This becomes a yi plus 1. So this is an I plus 1 of f, and everything else is the same. Okay. So all I did was change yi to a yi plus 1, and I divided by 1 over q. And for context, maybe you've heard of these before. These are known as de Moivre-Lustig operators. So these are de Moivre-Lustig operators. Okay, neat. Then we have another operator. We're going to call this one d plus, goes from vk to vk plus 1. And we have another operator d minus that goes from vk to vk minus 1. Sorry, these are the raising and lowering operators. So let me change the color. This is blue. So then the action here of f is going to be via plethism. So here the action is you're going to act by all these operators t1 through tk, and then you're going to take f and you're going to plethistically modify it. And then d minus of f is going to be very similarly defined. So it's going to be yk of f. You're still going to plethistically modify this, but you're going to multiply by something that's known as the plethistic exponential. So I'll explain what this is in a second. So this is minus y inverse kx. You're going to look at the coefficient of yk to the 0. So essentially the coefficient of 1. Okay. So what is this plethistic exponential? So here, this exp of x, right, is defined to be the sum over hn x from n equals 0 to infinity. And then taking the coefficient zeta, or this z to the r, is just taking the coefficient.
Either there's some lag time in my connection or your iPad.
Oh man, it stopped showing. Yeah. I don't know. I'm going to stop sharing and then I'm going to share again because sometimes it gets weird. Thanks for noticing that. Yeah, if it ever stops, just let me know because. No, don't do this, internet. Okay,
Oh.
there, good.
Yay, okay.
Yeah, thank you. Thank you for pointing that out. Okay. So this x is just basically multiplying by the sum of a series of hn. So here, if you have, minus yk, it's basically hn plothistically modified by that. And then this bar zr is just taking the coefficient of zr, obviously, in the Laurent series, z to the r. Okay, so then here, I should probably mention that we discussed briefly this C alpha at the beginning, but I didn't tell you what it was. So I'm gonna tell you what it is right now. So I should probably not say recall because we never really said that. So the CR of F, we're gonna define this operator, and it's going to be the following thing. So it's gonna be minus Q, 1 minus R. Sorry, this is very definitional, this section. So 1 plus 1 over Q times Z times, again, this plothistic operator, Zx, coefficient of Z to the R. And then you have a related operator, BR of F, X. So these will play a role in the proof, so which is why I'm mentioning them, obviously. So Zx, coefficient of Z to the R. So we have these operators. They were introduced by Hagelin, Morse, and Zabrocki as well, I think. And the idea here is that you define C alpha to basically just be the composition of the individual pieces, right? Where alpha is some composition. So C alpha J. And these two operators, C alpha and CR and BR are related in the following way. So if you set C of Z, let's say, kind of a series, to be Z to the CR Z to the R, then you have that C of Z. So the series is related to the series for B by taking B of Z and sending Q to 1 over Q, and then conjugating it by omega, where omega is the standard involution on symmetric functions, and then multiplying it by 1 over Q to the n minus 1. So it's kind of a heavy formula. You don't have to memorize this. The only reason I'm bringing this up is because we just talked about the plothistic exponential, and these things are defined using this plothistic exponential, and they're related. So at the end, when we actually get to the proof of the shuffle conjecture, which is very, very short, this relation here plays a big role, because remember that the shuffle conjecture, the compositional shuffle conjecture, is defined by taking nabla of the C alpha. So just keep these in mind. Now,
can you remind me what M is there?
M.
You wrote minus 1 over Q to the M minus 1.
Oh, actually, yeah, sorry. So maybe I know why. Let me actually not write this in terms of a power series. Let me just write this. So this is BM. That's why I have that BM. Sorry, I think I mixed two versions of the equality. So CM. Yeah, so maybe then let me get rid of this. That's what that M is. Thanks, Sylvie. I think I had two formulas and I mixed and matched them. Okay. Great. So then if we go back to our operators, these D alphas, or these D pluses and D minuses, then you can prove, so it's a proposition, to show that this D minus of YK I of F, if you act on this by D minus, it's equivalent to acting by this BI plus 1 of F. So this is a relation that is not that hard to prove. It's just a matter of using the definition of B, which, although it looks complicated, if you actually just like expand it out, it's not that hard. It's not that awful of a formula. And what this allows us to do is to basically reinterpret the shuffle conjecture, which is taking nabla of C, into taking nabla of B, which then you can translate to some sort of expression using these d minuses, right? Okay. And I should point out that here f is supposed to not depend on yk. Okay, sorry. So like I mentioned, this section's a bit heavy. So, okay. What kind of relations do these d's satisfy? So the ti satisfy Hecke algebra relations. So Hecke algebra relations, what does that mean? That means that if you take ti plus q, and then you take ti minus 1, this is 0, you get what are known as the braid relations. So these behave in the following way. And then if I and j are far apart, namely if j does not equal I plus or minus 1, then they commute. You get this kind of a relation. And again, the proof is very straightforward. It's just a matter of applying the definition and checking it. So here is...
Sorry, I have a question that I should have asked a minute ago.
Yes.
Your f comes from vk?
Yes, so f is a, yes. So f,
Yeah.
f is in vk.
Mm-hmm.
But it doesn't depend on yk. Like that's the condition. Okay, and then we have the big theorem, which I was hoping to prove today, but I'm so slow at this apparently. Is so here's the big theorem that relates all these crazy operators to these chi pi's that we were just talking about. Is that if you're given some dict path, which I'm going to just denote by north and east steps. So suppose we took A1 north steps, then we took B1 east steps, and so on, ... north, east, BL. Then you can express the function chi pi 1 for that dict path in the following way. But just saying, all right, I'm going to relate every north step to a d minus. So I'm going to apply d minus A1 times. And I'm going to relate every east step to this d plus operator. So I'm going to do that B1 times and so on, right? And so d minus AL, d plus BL, and I'm going to act on 1. Because remember, these are operators on these vector spaces. You need to feed them something. We're going to feed them 1. We're going to act essentially just by the order given by pi, by just relating, right, d minus with n and relating d plus with east. And the claim of the theorem is that in this way, you actually generate this function chi pi 1. And then as a corollary to this, we get the statement that if instead, to every corner, you replace every corner of pi with 1 over q minus 1 times the commutator of this, and then you leave everything else as north and east, with all other steps translated as above. Then what you recover is you get this function chi pi 0. So what do I mean by this? So if I take something like, let's say this path, right? So this has, if I do, according to the theorem, this is north, north, then we went an east, then we went north, then we went east. Well, I'm doing a terrible, sorry. Let me read this in a better way. So pi here is we do north twice, then we do an east, then we do a north, then we do an east, then we do a north, then we do an east twice, right? What that's telling us is that if we were to do a d minus twice, a d plus, d minus, d plus, d minus, d plus twice of 1, that this is supposed to be chi of pi 1. But if instead, and this is what the corollary is saying, we take these corners and substitute them with phi, right? So instead we do a d minus twice, but then we do a phi, or sorry, not a phi, what am I saying? Let me call this phi, just because it's, let me call this expression phi. We do a phi, and then we do a second phi for that second corner, right? So we're doing this corner first, then we're doing this corner, and then we do 2e steps, which corresponds to doing a d plus twice. Then the claim is that this is chi of pi 0. Now, these are not at all, this is not a trivial theorem to prove, and my goal for today was actually to prove this. Now, I have 10 minutes, so I'm going to try to start the proof because it's actually, it's a bit hairy, but it's cool how they do it. Any questions, though, before I continue with actually proving how this theorem is obtained?
One question I had was in the paper for the d minus definition, they took the coefficient at y sub k to the -1. Why are we doing y sub k to the 0?
Because there's two changes. So it's not just the coefficient that got changed. It's you'll notice that at the beginning there's also a minus y to the k
In our definition?
in our definition, which is not
Oh.
their definition.
I see. Okay. Okay.
Yeah, so it's
just
equivalent.
yeah.
When I was writing all these notes, I wasn't just looking at their paper. I was looking at the paper that Haglund and Gauche wrote, which is like an explanation of their paper, essentially an expansion of it. So some things are, it's kind of a mix and match of notation. So this is kind of why sometimes like the formula that Sylvie mentioned was a little bit mixed because I mixed incorrectly.
Got it.
But yeah, the version of D minus that I wrote comes from Haglund's version of the paper, not Carlson and Mellett, but it's the same.
Okay.
Yeah.
Thanks.
Okay, great. So then let's get to proving this. And sorry that today's kind of dry with all the definitions. So how do we do this? So wait, this was the exercise that I wanted to do. Okay, so how do we prove this? So we need to prove two things. But in order to understand what we're going to do, we're going to kind of have a bit of a setup. So let's do a setup. So we're going to let pi be, in dkn. And we're going to set sigma to be basically just a tuple of numbers, see sigma 1 all the way to sigma k, right? So just a tuple of numbers. And we're going to define this set, we're going to call u pi sigma to be the set of words. So such that wi is equal to sigma I for I less than or equal to k, and such that wi does not equal wj if I and j are in the area of this path. Okay, so here's our set, we've defined it, and associated to this set, we're going to define a symmetric function, or actually we don't know that it's symmetric, a function that is defined as follows. So this is basically do the same kind of a thing, right? Q to the n of pi w, xw, but now instead of summing over all words, we're just going to sum over words in this set. Okay, sounds good. And then the claim, and I apologize for skipping the proof, but the claim is precisely that this function is symmetric. Okay, It's non-trivial, but it's also not a very enlightening proof. It's just kind of a tedious, yeah, it's just kind of tedious. So, okay. The main point though, is that with this function, we can define a new function, which is going to be chi sigma of pi. We're going to define this to be the following thing. So it's 1 over y1 through yk of q minus 1 to the pi. Remember that this bar of pi was the number of north steps of pi times chi prime q of, oh, sorry, not q, I'm getting pi sigma of pi plethistically modified by q minus 1. So this is some crazy thing. It lives, so this is something that lives in vk. And why do we care about it? Because it turns out it's actually very useful in explaining how these d minuses and d pluses interact with taking north steps and east steps, right? Which is why we're starting pi is something that's already started at like level k. So here we're gonna denote some things. So if we have chi k of pi, this is going to be a special notation for when our sigma is going to be the tuple that's basically just the identity on 1 through k. You're just picking the first k things. So this is just for later, for shorthand. Okay. So in particular, we have that if k equals 0, right, then pi is just something that's starting in d0, which is basically saying you're starting at 0, 0, you're not starting up k steps. So this is really just pi is in k, which implies that chi 0 of pi, right, which is basically here, if we just substitute k equals 0, then this really is just chi pi 1. So this weird function is somehow generalizing chi of pi in these bigger spaces, right, in these vk's, right, because so far we had chi pi 1 just on symmetric functions, and we want to enlarge this to a bigger space. Okay, and so then the goal is the following. So the goal, in order to prove the theorem, we need to show that chi of k plus 1, right here, basically just taking the identity on 1 through k plus 1 of e pi, that this is just equivalent to acting by d plus on chi k of pi, right? Because remember that in our theorem, we want to relate plus steps with east steps and minus steps with north steps. So all this is saying is we're going to relate taking an east step to acting by d plus, right? And equivalently, we also need to show that if we acted by a north step, then this is the same as taking a d minus of k of pi. If we can prove these two things, then we get the theorem for free. Here, we're taking pi in dk. So what do we need in order to prove this? Any questions, though, at least about the structure of what we're going to do? So it's a bit messy because we just defined a bunch of sets and functions, but morally, all I did here is say we have chi pi 1, we defined it on symmetric functions, we need to extend this to something that makes sense on these bigger spaces, these vk's, right, with these extra variables y1 through yk. How do we do this? This is the way. It's not very intuitive, I understand, but this is just a definition. And all we want to show is that, look, on these higher level vk's, acting by d plus and d minus is equivalent to adding north and east steps. Does that make sense? So let's, in the last 3 minutes, see if I can tell you something about how to prove this. In order to prove this, we're going to need one proposition, so which I'm gonna tell you. So we have a proposition. So this is proposition 4.8 in their paper, and I will refer to it as proposition 4.8, which is why I'm giving it a label. So it states that if you take any word in, or any word, sorry, any dict path. I don't know why. Wow, W is a terrible. Let's call this something else. let's call this sigma prime somehow. So if we take any dict path, sigma, well, no, maybe let's call it pi prime. Sorry, let's call it pi prime. Yeah, any dict path pi prime, and any tuple, right? And if m is in, so m is an integer that shows up. So if m is equal to sigma I, for some I, with either m plus 1 not equal to sigma I for any, or sigma j for any j, or I less than j where sigma I equals m and sigma j equals m plus 1, if these conditions hold, then we get that chi prime of Sm on sigma of w. I'll tell you what this is in a second. Of course, I understand this is confusing. Chi sigma of pi. And I'm missing a pi prime here. Oh, no, sorry, I'm not missing a pi prime. This is supposed to be a pi prime. There it is. Okay, so what is this saying? If you're given a dict path, and you're given some tuple, and you have some m, whatever, that shows up in that tuple, but it satisfies the condition that either m plus 1 is not in that tuple or it's above it, right, in the ordering, so m is in a smaller position than m plus 1, then if you take that same sigma and you swap, so Sm is a simple transposition, it swaps m for m plus 1. So if you either swap m for m plus 1 or you flip their order, if they were both showing up in the tuple.
So it's acting on the values, not on the position.
Yes. Yes. So it's basically if you had m and m plus 1, it's just swapping.
Mhm.
Yeah. So it swaps the entries, right? Or it substitutes the entries of m plus 1 didn't show up, it substitutes the m for an m plus 1. Great. So if that happens, so if this is the kind of sigma that you're dealing with, then doing that operation is equivalent to basically taking your original chi and then acting on it by this tm operator. Kind of weird. And the proof is honestly really annoying and really long. So I'm going to skip it because you basically, the only thing you need here is this formula. Because what that's going to allow us to do is start with some dict path some sigma that maybe we don't like and basically flip it so that we end up with a sigma that is just a run like 1, 2, 3, 4, 5k, whatever, which will allow us to write, if we go back here, this proposition will allow us to write any sigma in terms of things that look like this, right? It'll allow us to take any tuple and write it in terms of things like this, because it basically allows us to flip the entries and get them in the right order. That's the goal of this proposition. So I am out of time now, and I don't want to keep us any longer. But basically, all that remains to prove in order to get this theorem is these two things. So questions? Apparently no questions.
And we're not going to say anything about the nabla operator?
Not yet. Not yet. It does come up. And the whole point, yeah, that's a really good point. So basically the gist of the proof is that you're translating all these combinatorial things that we saw on just symmetric functions over Qt, right? Like taking east steps, taking north steps. We're going to translate all this structure to operators on these VKs. So the first step is we're translating east and north steps to basically d plus and d minus. And then we're going to take the action of nabla to be some operator that's also going to act on these things. We just haven't defined it yet. So we're going to define an analog of nabla for these VKs as well, essentially. And that's going to be crucial in proving the actual theorem, of course. It's a complicated proof, so I'm sorry that it's taking so long. Questions? All right, in that case, I'm done for the day because I don't want to keep us any longer. I'm happy to continue ranting,
Let's
of
thank
course.
the speaker.
Thank you guys, and again, sorry that that was a bit long and dry. So I was thinking we could do an example, or we could do an exercise to actually prove that chi of pi 1 is symmetric. If you're interested in actually playing around with that. Or alternatively, we could also try to actually compute an example of this theorem and do an example of this. Basically, given a Dick path, let's compute the symmetric function that you get by applying d plus and d minus. So it's whatever you guys think is more helpful. I'm going to let Foster decide.
I have a preference, but I feel like students should speak up first.
No student is speaking up, Monica.
Oh, I'm so sorry, my internet is a little bad. Yeah, I'd be happy to work out some examples and exercises.
Do you have a preference, Foster, between doing either an example of d plus or d minus or proving that chi of pi is symmetric?
The chats are Raymond and Jinping are both going for example.
Okay, well then let's do
and
that.
by example, that means the d plus d minus
Yeah,
stuff.
I think examples are good.
Let's do that then. I agree.
Okay, I could start screen sharing if you like. And
Yeah, let me stop sharing.
okay, if you have suggestions on which examples would be good to do, what would be instructive, that would be great.
So let's do a small example, and actually let's do an example that I know the answer to, so that we can check whether it's right or wrong.
So just like maybe n being 2 or 3 or something.
Yeah, there's a small example. Give me a second. Let me just check it. Okay, yeah. So let's do this example. So you take 2 north steps, then 2 east steps, then 1 north and 1 east. So it's a 3 by 3 box. 2, 2, 1, 1. Exactly. Let's do that path.
Okay, so this is our pi, and we want to figure out.
Can you write out n and or like, n squared e squared, just because we'll need it later.
Okay, yeah. And then according to the theorem, chi of pi 1 is going to be the north steps turn into d minuses. Maybe I'll just write d minus d minus.
Yeah.
Of 1. And maybe I'll remind everyone. So let's see, d plus. Let's see, so d plus goes from this to this and is defined by
I have a naive question. If the path is not a Dick path, and I apply my series of operators d minus d plus to 1, will it give me 0?
If it's not a square, like if it's like in a rectangle?
No, if it goes under the diagonal.
Oh, that's a good question. I don't know, actually.
Oh. Yeah, I mean, I know if it's above the diagonal, it's just whether so V0 is symmetric things. So if the pluses and minuses balance, you land in V0. But if they're, skewed, you have like too many north steps at the beginning, you'll land in like a VK.
So I mean, the question is equivalent to saying like, what is the action of D minus on V0? And I think D minus on V0 is defined to be 0.
Yeah.
Okay.
So that it's consistent, yeah. Because it's like the lowering operator and there's no V minus 1. So, yeah.
Hmm.
So I would actually, and this is just a suggestion, it might be beneficial before we start computing anything to maybe rewrite D plus and D minus, especially D minus, to something that's a bit more, I don't know, like actually maybe write instead of X, write like the sum of H plothistically modified by something. But maybe, I don't know, you can do it later.
Okay. So let's see, this is
And there's a minus sign, right? Or did you write the minus sign?
yeah, it's there.
Okay.
Okay, are we imagining that this all happens in a fixed, what's K?
The K starts at 0 and then it's moved.
K is the space that you're in. So 1 lives in V0. So when you apply D plus to 1, so you have to keep track of K, right? D plus applied to 1
Okay.
means that in that operation, K is 0. But then when you apply D plus to D plus of 1, D plus of 1 lives in V1 because D plus bumps your K up by 1.
Okay, thank you.
Mhm.
So do you think we should just do this from the definition and just start computing?
Yeah. It's a little bit annoying, but once you get the hang of it, it's not that hard.
Okay, sounds like a plan.
So I will tell you.
Okay.
I will
Anyway,
tell you-
Don't worry about color.
I'll give you a hint just because I know what. So D plus of 1 is always 1. So you can go through and check this. Maybe you should, but D plus of 1 is always going to give you 1.
Let's see. So I wouldn't mind reasoning through that. So K is 0.
and in
so
my
we're
function, I
going
replace
to-
any x's by these things.
So 1 plothistically modified by anything is just 1. And then the TIs, and this is a property of the TIs, if you feed it something that's symmetric, it just spits out the same function. Because the TIs are essentially kind of symmetrizing, let's say, your function 1.
And also in your definition of D plus, there's a Y. And I think your handwriting looks like it's a Y I plus 1, but I'm pretty sure it's a K.
YK, yeah. So that's kind of why D1 of 1 is always 1. It's just because it basically falls through everything and nothing acts on it, interestingly.
So this one lives in this. I need to remember that K equals 1.
So maybe if you want to write, K equals like in each, like maybe to the left or to the right, so we keep track of K. In the first line, K was 0. In the second line, K is now 1. Is that clear to everyone? Because I think this is an important point that why we're keeping track of the Ks and why they change. Good.
Okay, so we're thinking about this coefficient of this. So I suppose that is taking out the H1 term.
So
So let's see.
I think you get E's, right? You get an elementary.
Right. So I guess the Y's cancel out and the negative sign should also cancel out. So this would be like, okay, so I think this is either that or maybe I'll just write round brackets.
Yeah.
Or that or any of them, whichever one you like.
Yeah.
Okay, at this point K has gone back down to 0. So now I'm taking D plus of this thing. Are people happy so far?
So maybe I'll just say a few words, right? So the idea here is that the y1 to the -1 just comes out of hn because it's homogeneous, and then you end up with like a y1 to the n or minus n hanging out in front, and then hn platistically modified by minus x is e, which is why you get an e1 when you write the coefficient. So that's just kind of like why he just said it was h1 equal to e1 equal to s1. That's, and then of course, when you take the coefficient of y equals 0, you end up with that y1 inverse, which cancels with the y1 at the top, which is why you don't get any coefficients of y. Okay, good. Thanks, Foster.
Oh, yeah, so let's see, you said that hn negative x like this.
You just get en, right?
Oh, do you?
I think so. If I remember
If you-
modification correctly, maybe I'm crazy, but I think so.
But then why did you lose your minus sign then?
Oh, maybe you're right.
I think, do you get negative?
I think it's -1 to the
Maybe
n
that's
plus or -1, because remember how the power sums go with
Yes.
x's.
yes, you're right. It's -1 to the n. Thank you. That makes more sense. Yes, definitely. Yes, you get a -1 to the n in front.
Okay, well, if everyone agrees, then. So I guess now we're taking d plus applied to k is 0, so we don't have any of these. So I don't know, do people like h's, e's, or s's, or p's?
Not p's. Get rid of p's. P's suck.
Let's maybe stick with E because morally that's what spit out.
Okay, maybe I'll just write okay, e1 plus e minus 1 y1.
Okay, so if we think of E1 as P1, I think
I know that when we do plethism, okay, I'm not entirely hearing everyone. When we do plethism,
We're not entirely hearing you either.
oh, okay, maybe it's better now.
yes.
We're supposed to have some idea that certain things are variables and we replace, when we do plethism, we replace the variable. We're thinking of the x as also the y. Is that?
So I'll give you a hint. This plethism, like pk modified by x plus q minus 1 y1, sends pk to pk plus q to the k minus 1 y to the k, if I remember correctly, which would mean that E1 plus modified.
Maybe you shouldn't say K because here K is 0. Maybe, PM.
Yes, that's what it's done. Yeah, PN. I'm just saying in general that plethism is that's what it does on power sums.
Yeah. Yeah, right.
Thank you. Yeah, that's what I wanted to write. Thank you, Foster. Exactly.
Q to the M. Q to the M.
Yes, Q to the M.
Yeah.
Yes.
That seems like that.
Mm-hmm.
So then we're going to do another d plus to this. So this time we've got a t here. We've got t1, and then we're going to do, okay, so that's a constant. So t1 applied to, and then I guess it would be e1x plus another one of these. Or no, this time it's y2. So e1x plus that and that. Okay, so let's see these TIs. Maybe I should find some other place to put this. Okay, I might not have enough space here. Let's just do this.
Can you do it in a different color, maybe? So it's like clear that it's like a separate computation.
Okay, I can do that.
Oh, I think he froze again.
I think he froze too.
Foster, come back.
But like you said, if you have something that's symmetric,
Mhm.
then T1, you
So-
should do nothing to it or multiply it by Q, something like that.
Yeah, so E1 ends up just kind of passing through, right? Because nothing happens. So the SI of F leaves it by itself, like leaves it alone. And then you end up with yi plus 1 minus yi. Oh,
Uh-oh.
gone.
Oh, dang. Bad day for his internet to be down.
Okay, let's give him like a minute or two to come back.
But so when the T acts on the E, because it's symmetric in the X's, it doesn't change anything.
Exactly.
But we still had that Y1 and Y2 stuff.
That's what ends up getting affected by the TIs a little bit.
But it's a Q minus 1 basically times Y1 plus Y2, which is symmetric in Y1 and Y2, so it should also stay the
Just
same.
pass through. Yep.
And it doesn't get scaled multiplied by a Q, it really just, because sometimes depending on how Heck algebras act, sometimes the T.
So the TI is not scaled, the TI inverse is because they pick some stupid normalization for the scain relation.
Yeah.
Okay, sorry, my internet connection is really unreliable.
It's okay.
But here we are. Okay.
While you were gone, we just
solved it. We're done. Thanks, Foster.
T1's gonna actually be on that.
Okay. Would you please tell me what you figured out?
So I think you can just write the same exact thing without the T1 there. And that's what you should get, because I think T1 just acts trivially on that.
Okay, because there are symmetric functions.
They're symmetric in yi's, essentially.
So just so I'm understanding, the SI is flipping.
Yi and yi plus 1.
Okay, just the y's, not the x's.
No. So the TI is really just acting on the y's. It doesn't care about x's. So anything that's symmetric in x's just goes through for free.
Okay. So now k is 2, and now we're applying d minus to this. Okay. Minus q minus 1 y2. Okay, so I guess that just goes away. Are people happy?
Could you scroll up just one high? I just want to look at the D minus upstairs for a second. Okay. Okay. Yep.
So I guess that first factor doesn't really come into it, and it's the same sort of thing with the other term. Let's see, so I guess when we did this, we just got another symmetric function. So maybe, is it going to be just this? And then times another one of these.
I have a question though. So when we say the coefficient of y2 to the 0 in that whole thing, right? It's
So the y2 in front should affect it.
right. But does the y1, I guess is my question. So when you say y2 to the 0, does it really mean you're just looking at powers of y2, or you're looking at all polynomials in y's, meaning it's also like, well, y1 to the 0, y2 to the 0?
No, I think you should just be looking at coefficients of y2. Yeah.
Okay. Okay, so then it should just, right.
That looks right. I think.
Okay. So yeah, we're almost done. We just need to apply d minus one more time. Okay. So let's see, this time k is equal to 1. Let's see, so should we maybe multiply out these symmetric functions? And should I write them in terms of p's?
For plethism, probably.
Okay, so let's see, e1 times e1. I'm good with h's, e's, and s's, but I'm not very good with p's.
Well, it's just P1
Well,
times P1.
P1 is
square.
P1.
Yeah.
Yes.
Oh, okay, good point. Okay, so p11, and then maybe I'll just leave this other one the way it is. Okay, so d minus applied to this means I need to take negative y1, and then I need to plethistically,
X minus Q minus 1, Y1.
Are we missing a term? Sorry, in like the previous computation?
oh, these things are possible.
Well, he did the reason why the Q minus 1, Y2 went away was, right, in the plethism, it just it subtracted it back out.
Yeah, when I did this, there'd be like a plus one of these and then a minus one of them.
Mm-hmm.
So so that's okay, right?
Why did you get a minus? Sorry. Because it's minus. Yeah, I guess it is minus. You're right, you're right, you're right, you're right. Yeah.
That bit there. I mean, I don't know. This is my first time doing it, so.
No, so I agree that the Y2 should go away. I'm just wondering, because we're supposed to be, we should get an extra term, I guess is what I'm saying. We should be getting an E or an H2 or something in there, which is why I'm wondering why it's not showing up.
Could it be folded up in the P11 compared to the way you
No,
had it?
so what we're supposed to be getting in that last step, which is why up to there we were perfect, we're supposed to be getting H2 plus E2. Oh, H2 plus E2. Never mind. It's a P11. Yeah, never mind. You're right. We're all good. Sorry, Foster. I don't know how to multiply symmetric functions, clearly.
Oh, yeah. Yeah, I'm better with the S's, E's, and H's. And yeah. Okay.
Thanks, Monica.
Right, so P11 is, I guess it's
It's H2 plus E2, of course.
Yeah.
Yeah.
Okay, so let's see, negative y1 times this thing with the minus q minus 1 y1. I guess, let's see, what should I write? Maybe just large bracket here. And then, of course, I'm sure that simplifies quite a bit, but for the
Actually,
time being,
if we
hopefully
had
I'm writing
kept it,
something correct.
if we had kept it as sort of the E1 of X plus Q minus 1 Y1 all times E1, then could we have done, since we're going to do the minus Q minus 1 Y1, it would have become just a plain old E1 of X, and then we would have the E1 of X. well, never mind. Okay. I think it's going to come out to the same thing.
Oh, so I should have just left it like that.
Well, I'm wondering if we should, in the same way with the q minus 1 y2, it went in and then it went away.
Mm-hmm.
I feel like it could have done the same thing there. And then
Yeah, I think it's the same thing, right? Because E1 is
put this into the homomorphism that way, right?
Yeah.
Mhm.
So is that plethism just the same as this?
no, because you have to apply it twice, right? You multiply the two things, so you should end up with like a y1 squared somewhere.
Hmm.
Right?
Okay, so that's
Yeah.
P1
Yeah.
times P1. So like that, and then another one of them.
Yeah, and then just squared, exactly. Yeah, that's what it is.
Okay, and then this one is just one of these minus one of those. And then we've still got this stuff. And probably, yeah, what Monica is saying. Yeah, so that one of those terms cancels out. Okay, but in any case, so P1 of x squared. Okay, so I guess I'll write P11, and then maybe I'll write this. And then that'll cancel out with that. E1 and P1 are the same. So maybe I'll just write that as minus just one of these.
Did you forget a y1 squared term?
I think this term cancels out with this term.
Oh, sorry. Yes, of course. I thought you were talking about the other term that was canceling, not that one. Yeah.
Okay, so maybe I just have that. And then okay, so I guess I'm going to pull out different terms from this summation for each of these ones.
Mm-hmm.
So I guess this one on the left, maybe what I want is P11 times H1 or E1
Or P1 or
or
whatever. Yeah.
P1. And then with this other one, I guess maybe I want an H2 and
And the sign is going to flip,
okay.
right?
Let's see. Well, I've also got a minus sign here, so I'm not quite sure which one it's going to be. But
Right. I think
I think we have a minus sign because it's -1 to the end we decided. So if it's n equals 2, right?
right, but there's a minus y1 all out in the front. And then there's a minus sign there, and then there's a minus that comes from there.
But I think the minus from inside the sum is -1 squared. No? Maybe not.
Mhm.
So maybe
I
plus.
think so.
yeah, I'm also not sure. I had a feeling that when we do this, we're supposed to imagine that our alphabet is -x1, -x2, when we replace the x1 by -x1. So I thought it was supposed to be something like that was just negative without the to the n, but I'm not sure.
See,
I think the sign should be flipped from where it is currently.
You want me to change it to a plus?
Well, only if other people think so.
I'm not really
Right.
sure.
Okay. Because I was thinking, well, with the, right, the first term, I mean, we have a minus y1. And then we're picking up another minus y1, like inverse from inside there. So we get a total overall plus. And then I feel like when we go to the quadratic term, I don't think we have a negative there, but we still have the minus y1 and the minus q minus 1. So, but I guess Nicole has it worked out somewhere else. So in the end, we can check if it agrees.
yeah.
Maybe I'll
Yeah, just
use
write
the
it.
functions.
Exactly.
H2 E1. So that's like an S3 and an S21.
Mhm.
I'm a fan of share functions. So maybe that's what we get.
Your Q. Oh,
We could check it against the pi of
so you're supposed to be
one.
getting Q S11 plus 1 plus Q S21 plus S3. So your Q should be on your S11, not on your S3. That's what the answer is supposed to be. And I want to say that maybe should that H2 be an E2 maybe? No.
When we do this thing
Yeah,
here,
I don't know. I'm just sorry.
that would make it be this answer, it seems.
Here, you were right.
Yeah, how did you get H2 and not E2 in the second part of the sum? Yeah, that one.
Okay, maybe that's an E2 then.
Oh, because of the minus sign.
Yeah.
Okay, so that would give us that. And yeah, I think I like Monica's idea. We can check it because that's supposed to be chi of pi comma 1.
Exactly.
So yeah, if I draw this again, north, north, east, east, north, east. So this is sum over all words.
Let's see, and here n is 3.
Well, let's see. If we know that it's a symmetric function, I guess we can calculate it in terms of the m's by just thinking about words with partition weight. Alternatively, well, you told me that it's an LLT polynomial, but maybe we won't pursue that approach.
I think you're the only one who's familiar, or maybe not the only one, but you're the most familiar with LLT polynomials.
So let's see, I guess the possible words of partition weight. I could have like a 3, I could have a 2, 1, I could have a 1, 1, 1. Wait a minute, is that what we're supposed to do? Yeah, I guess we look at the ones with partition weight, and then these are the coefficients of the monomial symmetric functions. Okay, so how do I figure out inv of pi comma w?
So we need to we need to look at the definition. I don't know how to do it quickly, sorry.
So are we going to think of 1, 1, 1 as like W1, W2, W3? And then we're just going to look at, we have our corners, and then we're going to look at like the 1, 2 versus 1, 3 and so on.
Yeah, because inv was like sigma applied to div. So we could in theory, figure out what div was and then just permute them. But I guess it doesn't matter because inv is the same number, right? It's just inv is just div. Because it's just counting the number of cells that show up.
Do you want me to write these numbers in here and then
just count like div, yeah.
Okay, so I think that would give me 0. So then I get just an M111, or no, an M3.
Doesn't
Okay,
everyone agree, right?
So far that's good news. And then if I do a 1, 1, 2 like that. Okay, it's been a little bit of time. Is it going to be a 1 this time?
Yeah, I can't do div without looking at the definition. I'm so bad at just doing it quickly like you, Foster. So
yeah, I think
Well, you
maybe
can
this
see the
2
1
and
and the
this
2
1
are in adjacent diagonals.
Maybe it needs to be the other way. But I think one of the ways will give us 0 and 2 of them will give us a 1.
Mhm.
So maybe this gives us a 2q plus 1 m21. And then, let's see.
Your ability to
Uh,
go div are impressive.
hmm.
So the only contributions of din, so nothing's on the same, oh no, sorry, the 1 and the 2 are on the same diagonal. So, but they're always, when we have 1, 2, 3, those are always going to be different numbers from each other. They'll never be the same. So we only need to look at the 1 and the 2 on the off diagonal from each other and count when one number is higher than the other. And so that's either has to be like the pair, like 1, 2, or 2, 3. And so, right. Except I can never remember the higher or the lower, which is supposed to be what. But
Yeah, I'm not sure if I have it right. Are my inequalities kind of going in the right direction, or should I change one of them?
well, they can't both be in the same direction. I just don't remember which is which.
So, oh goodness.
I might have made a mistake in my notes before, so
No, and the one weird thing that trips me up is the switching of the J prime and the J. So if we have to get div of pi w from div of pi first, right? It's like the strict subset.
Yeah, so we need div of, well, div of pi w is just like, oh yeah, I guess you're right. Oy. All right, it's 12:40, so I'm gonna end it, and I'm just gonna say, check it and make sure it works. Exercise to the take home exercise. Check that it works. It should.
Yeah, 5q plus 1 just doesn't.
oh, that was just a
Yeah.
guess. I'm not really sure.
Okay. I mean, if I'm just looking at the S3 plus Q plus 1, S2 1 plus Q plus 1 1 1 and working from there and thinking like, let's expand that.
have to be?
Pardon?
What does it have to be, basically?
Yeah, what does it have to be? And then back solving from that.
All right. I'm gonna let you guys. I'm gonna end the meeting just because I think we're way over time. Unless you want to stay and work through, that's fine too. I'm gonna end the recording now.